Hi, I'm Mike Freedman. I'm going to talk just for a few minutes to you about quantum mechanics, the potential for a quantum computer, the mathematics, physics underlying it, the fantastic engineering constraints, materials growth constraints, all the problems we face, the problems in building a quantum computer, the problems in figuring out what the heck we're going to do with it once we've built it. It's sure a load of problems, but it's a fascinating and beautiful subject. I'm the director, actually, of Station Q. This is Microsoft's research station for exploration of the science, the mathematics, condensed matter physics, and computer science behind quantum computing. We put it together because we wanted in an environment where we could attract the best theoreticians to work on beautiful abstract problems of laying the foundations for the mathematics and physics of what eventually will be an era of quantum computation. Modern computer algorithms executed on present-day computers use probability quite a bit. But in quantum mechanics, there are things called amplitudes, which are more subtle versions of probability that can actually interfere or support each other. Both are possible. And a quantum computer will harness these effects, they're called interference effects, to make more sophisticated information processing and will enable us to solve certain selected types of problems exponentially faster. In the world we live in, it's conventionally conceived as three-dimensional, though you could say time is a fourth dimension, but with three spatial dimensions. But in quantum physics, it's possible to produce very good simulations of two-dimensional worlds by, for instance, confining a gas of electrons within a crystal interface. They're crystals which are grown to have a purity of 4 nines. There are only a few laboratories that can grow crystals with this precision. Some of these are in Germany, some are in the United States, in Princeton. Quantum Hall physics is based on this. The mathematics which describes quantum Hall physics is really pretty nearly exactly two-dimensional. For processing quantum information, we've been led to think about two-dimensional systems. Even further reduction to one dimension is possible, and people have conceived of topological systems based on very fine nanowires of exotic materials interfacing with superconductors. We collaborate with experimentalists who are developing cryogenic systems for processing and storing quantum information. They're referred to as Majorana systems, and physically what they are is they're tiny wires, nanoscale wires made of indium arsenide or related 3-5 semiconductors with a large spin-orbit coupling, and these are coated over part of their domain with a niobium alloy superconductor. And the physics of this sort of sandwich of semiconductor and superconductor produces exotic excitations, and these excitations at the interface carry topological information, the so-called Majorana zero modes. Quantum systems are notoriously delicate. If you touch them, you upset them, and they behave differently. So you can't observe a quantum system and expect it to carry on as if it was unobserved. So there's a paradoxical requirement of both exquisite isolation and control of the quantum system. Because the delicacy of a quantum state, the whole process has to be carried out at extraordinarily low temperatures. 0.03 of a degree above absolute zero is a typical operating temperature. 0.03 of a degree Kelvin, as opposed to the background radiation of the universe, which is about 3 Kelvin. So if you went deep into interstellar space, it would be 100 times warmer than in the laboratories at, say, Delft University or the Bohr Institute in Copenhagen, where our collaborators work. In addition to the low temperatures, in order to exploit the spin-orbit coupling, modestly large magnetic fields of more than a Tesla have to be applied to these wires. The temperatures, the magnetic fields, the sample purity, the exotic materials, indium arsenide, high spin orbit semiconductors, alloyed superconductors. It's quite an exotic zoo of materials and special experimental conditions that are necessary to get off the ground. I think the beautiful thing is that most of the work is still well shared, and even though the efforts have separate roots, there's a expanding international consensus of what are the promising systems and what are the promising approaches down this road. You know, one of the things that you always ask with a new technology is, well, if it's so great, why isn't nature doing it in some corner of the world or some corner of the universe? And you might wonder if the quantum computer is the right way to process information. If we should do it quantum mechanically, you know, why aren't our brains quantum mechanical? Or, you know, why don't we see this happening somewhere? And the answer may be that the universe as a whole is just too warm to manipulate quantum information efficiently. The universe, though it explores the high extremes of temperature, doesn't have any natural refrigerators in it. And the coldest places are actually on Earth in laboratories. But maybe in 100 billion years, the universe will cool down and go in that direction. I have a lot of confidence on general grounds that quantum computers will be very powerful, very important. But I can't say exactly what they'll be good for. So the reason I believe in their ultimate strength is because of the philosophy of how they use information. They process information using quantum mechanical amplitudes, and probabilities are sort of the ghosts of amplitudes after they've been degraded to our mere classical world. The quantum world is really the elegant, the precise, the unitary world. And the classical world we live in is sort of a corrupt shadow of it. So it's very easy to believe on mathematical and philosophical grounds that quantum mechanical processing of information is the key. You know, at some level, all that's important about us is what we think. And computers expand or transform what we can think about and how we think. Now, what the ultimate relationship is, I think, is a subtle question. Science fiction writers have explored it. Chess players have explored it. You know, computers beat people at chess, but pointedly, the combination of a person and a computer is better than either one separately. This is well known in the chess world. But what we do know is that quantum computation is the uncorrupted, it's the sort of lossless, frictionless way for a machine to think. And once you have that idea in your head, it's very hard to go back to ordinary computation.